So this is the kind of problem that we've been doing recently, where if we want to know the slope of the secant line, we end up using our difference quotient here in order to be able to find the slope. Because remember, the difference quotient always gave us the slope of that secant line. And so, for instance, you may recall this problem from assignment number 23, one of our recent ones, where you found the slope of the secant line through this point and some other point that was on F, some other one that we ended up picking. We then extended that with that same equation, where we then use that to estimate the slope of the tangent line. And remember, in order to find the slope of the tangent line, basically we're taking that whole idea of the 2 plus h and making h smaller and smaller and smaller, visually speaking. It's like we were taking this graph, so this was our original function graph here, and we were finding the slope of the secant line through those 2 points, so this one and whatever this other one was, and we kept trying to inch that closer. So this tangent, or this secant line, was closer to our actual tangent line slope, and then when we moved it even closer, it was yet even closer to the actual tangent line slope. And so basically what we kept doing is we kept bringing h closer and closer to 0. Well, today we're actually defining that idea in terms of a limit. So notice that what we were really doing all along is we are taking our difference quotient here and we are finding the limit as h approached 0. And that was telling us what the slope of our tangent line was. And so really that question back here where it said find the slope of the tangent line at x equals 2, it was really giving you this problem. It was telling you find the limit as h approaches 0. Now that limit as h approaches 0 of the difference quotient has a very special and important name for this class. This is going to need to go into your notes. That is actually called the derivative. Now this idea of the derivative is super important in this class. In fact, you could say that really this class is all about derivatives. And that's our main focus of what we're going to be dealing with here. So this idea of what a derivative actually is going to be a huge deal. Now, a little bit more detail here. First up, when we see this, it gets written as f apostrophe a. How do we read that? We read that as f prime a. So that little apostrophe there ends up meaning prime. Basically, it's generally used in math to talk about anytime we do something to something and it's the result. But here, you're going to see it basically always used in relation to the derivative. Okay, so f prime of a means the derivative of f of a, and we can find that by finding the limit as h approaches 0 of the difference quotient. Notice this stuff down below now, and if you didn't already make note of it, this would be the time to do so. Notice that these two questions are actually saying the exact same thing. The formula itself doesn't matter so much, but the words, the instruction words do, and are definitely worth making note of there. To say, find the slope of the tangent line as x equals 2, means the exact same thing as to say, find the derivative at x equals 2. In other words, the derivative is the slope of the tangent line. And the slope of the tangent line is the derivative. Now this is tangent line, not secant line. So now we're getting very specific into tangent line. So after going and doing a whole bunch of individual derivatives with some with the same function, some with the same x value, I want to take a look at this particular problem. So here I have a function f of x that equals x squared plus 4. And I'd like to find the derivative at each of these different x values. Which means, technically speaking, what I'm doing is I'm finding the limit as h approaches 0 of that difference quotient every single time with plug the number of x in for a, plug x in for a, plug x in for a, over and over and over again. But there is a more efficient way to do this. What is a more efficient way to find all of these derivatives? So yes, exactly. A great way to do this is rather than starting every single time by plugging the number in, instead, why don't we just leave this as x plus h, get the equation of what all that stuff is going to work down to, And then once we have that, then we can just plug in the -2, -1, whatever. That is actually how we find the derivative equation of f of x. And this goes into your notes. This would be like the biggest part of your notes for today, the part that's going to be used the most often, because oftentimes we really want to find the equation of the derivative. And this is how we do it. We do difference quotient, but we leave the x in there as an x. And then we find the limit as h approaches 0. So now I'm going to go back to that problem that I was asking you about a minute ago, and we're going to find each of these derivative values. But rather than plugging in the -2, the -1, the 1 all individually, we're going to start by finding the equation of the derivative. So we're going to go over here and we're going to say f prime of x equals the limit as h approaches 0 of, and now plug that into the difference quotient over here. Now when you plug it in, make sure that you do minus parentheses f of x. The most common mistake I still see when doing these is forgetting that we're subtracting both of those pieces. And so then this is what we're going to be figuring out first, is we're just going to take this difference quotient equation and we're going to figure out what all that simplifies down to. So on your own, take it from there, figure out what that equation is going to give us. And so when we end up working all this down, we simplify the difference quotient portion. It gives us 2x plus h. And we're still finding the limit as h approaches 0 of that. And so then f of x is going to equal, now we find that limit. So we can go ahead and use direct substitution because it's just a polynomial. So I plug 0 in for h. That leaves us with 2x. And so then that is our derivative function. F prime of x equals 2x. Which then makes our life a lot easier for doing those other problems there down the left-hand side, because now they all should be super easy. What is f prime of -2? -4, because all I'm doing is I'm just plugging that -2 in for x in my derivative function. And so then I end up getting -2, 2, 4, and 6. And then just one other thing to bring back and just remind you of, remember what the derivative means. The derivative here, f prime of -2, for instance, means the slope of the tangent line when x is -2. So if I went to where x was -2 on this graph over here, I would find that the slope of that tangent has a slope of -4. And then that can be true for any of these. So it's also telling us stuff about the graph as well, just to remember that that's the slope of the tangent line. So find the derivative equation of this function, and then once you've found that, go ahead and find those two derivatives given down at the bottom. Okay, and this is what we should get for our first step. And again, as you write that in there, make sure you're remembering these parentheses around the minus f of x part. That way you'll help yourself to avoid that big error that can happen when we subtract both of those terms out. And so in this case, we end up finding that g prime of x equals the limit as h approaches 0 of 3. And of course, remember that when we're dealing with just the limit of a constant, the limit as h approaches 0 of 3 is just going to be 3. Which means then that there's questions down at the bottom. Find g prime of 1. G prime of 1 will equal 3. And g prime of negative 3 will equal 3. And so every single derivative of this, every single value is going to give us the same thing, which I want you to see should make sense, and we almost should have seen it coming. Because remember, the derivative means the slope of the tangent line, right? If I were graphing the original function up here, what's the shape of that graph? It's a line, right? Does the slope of a line ever change? No. The slope of the line is a constant, in this case, 3. And so it should have made sense that, yeah, it's just going to equal the same thing no matter what it is. The slope of our tangent line, that is our derivative, is always going to be 3. Now this one will not be a constant. Go ahead and please find the derivative of this function and then find the slope of the tangent at x equals 3. And I just noticed something in my work. What is missing in my work here? Yeah, the limit. Get in such a habit of using difference quotient, we still got to write that limit out in front of it. So I got to go make some room and put that back in there. There we go. That's more like it. That's more what we should be seeing at each step along the way. Alright, so to finish this problem out, you should have found a function for our derivative, f prime of x, equals 10x plus 6. And so then I'm going to take that x equals 3, and I'm going to plug that in there. So basically I'm doing f prime of 3 equals 10 times 3 plus 6, so that's going to end up equaling 36. So our derivative ends up equaling 36. That's a pretty steep slope, right? Because that's what it's asking for. The slope of the tangent line is x equals 3. But yeah, that's exactly what it is. It's a very steep slope of 36. All right, then on to our next question, where perhaps there will be a few more questions. We haven't done a difference quotient with a square root yet in here, so it'll be good to see how to tackle this. All right, so if we're going to start by finding the derivative equation of this function, I'm still going to start the same way as I always do. I'm still going to set it up using the difference quotient and find the limit as h approaches 0. So go ahead and plug this function into difference quotient. And so you notice when you plug it in difference quotient, f of x plus h, well, it's still just plugging x plus h in where there used to just be an x. And then minus f of x, so minus the same old equation, over h. It just doesn't look the same as what we've seen when we've done difference quotient with polynomials, but it's still putting it into difference quotient starting at that same kind of way. Now we get into the part that's going to be different on how we simplify our difference quotient. How am I going to deal with it? What should we do? Remember earlier this year we were trying to figure some of these out, and we had to multiply by the conjugate? That's what we're going to do. We are going to have to multiply the top and bottom by the conjugate. So there's multiplying the top by the conjugate on the top. And of course, whatever we do to the top, I'm also going to have to do the same thing to the bottom. And the beautiful thing about multiplying by the conjugate is it's actually going to make the top a lot simpler to work with. The bottom is going to be a little bit uglier than it started out as, but it's still going to be workable at least. So let's start going through and seeing what this gives us then. The idea of multiplying by the conjugate is that when you multiply conjugates together, you basically end up squaring the first term and squaring the second term. And so if I square this square root of x plus h plus 1, squaring the square root makes the square root go away, which means that that just becomes x plus h plus 1. Then it's going to be minus and square the second part of the conjugate. And in this case, that's squaring the square root of x plus 1. And if I square the square root of x plus 1, that gives me x plus 1. Now, a little detaily trick here. I don't want to write it like that. I want to write it like this with parentheses, because I'm subtracting the whole x plus 1 here. And if we don't put those parentheses in, we're not going to handle that minus with the 1 appropriately. And then this is all over. Well, the h is still in the bottom, but it has a lot of company now. That h on the bottom is now being multiplied by that conjugate. So it's multiplied by the square root of x plus h plus 1 plus the square root of x plus 1. Now, certainly the bottom is a lot uglier than it was before, but just leave the h outside of parentheses and leave the conjugate inside the parentheses like I've shown here. It's going to make your life a lot easier going forward, because our hope is that we're going to be able to cancel that h out, and this is how we're going to be able to see that we can do that. All right, now from here, go ahead and simplify on the top. Now notice on the top, I can end up doing the x minus the x, and I can do the 1 minus the 1. So on the top, it just ends up equaling h. We're used to these things working out where we just have an h on the bottom. This one ends up giving us just an h on the top. So it's h over, and then the bottom is untouched. I haven't done anything with that. And now that we have it to that point, what cancels on the top and bottom? H, right? Now when I cancel the h out on the top, what is left? 1, absolutely. So then this whole thing ends up working out to be the limit as h approaches 0 of 1 over the square root of x plus h plus 1 plus the square root of the x plus 1. And now I can go ahead and find the limit as h approaches 0 because I no longer am multiplying the bottom by h. So it's no longer going to cause us to divide by 0. So direct substitution works. So f prime of x is going to equal 1 over, well, in that first square root, if I plug 0 in for h, it becomes x plus 1 plus the square root of x plus 1. And so on the bottom now we have 1 over x plus 1 plus x plus 1, square roots. Well, notice it's the same square root plus itself, right? So then I can actually simplify that just a little bit, and I can make that 2 times the square root of x plus 1. And that's just a little bit simpler for doing that work on the bottom. That is our derivative function here for our square root. Now, having done that, we can now find the slope of the tangent at x equals 8. So, do so please. Figure out what is the slope of the tangent at x equals 8. Alright, so we end up doing 1 over 2 times the square root of 8 plus 1, which of course gives me 9, so it's square root of 9, which is 3. So the whole thing ends up equaling 1 over 6. So the slope of our tangent here at x equals 8 equals 1/6.